Welcome back to Heraverse, where deep space mysteries meet clear, grounded science. In today's video, we dive into one of the strangest visitors our solar system has ever seen, interstellar object 3I Atlas, and the massive debris stream Earth is about to pass through. If you love calm, detailed explorations of cosmic puzzles, make sure to hit the like button, subscribe to Heraverse, and turn on a notification bell so you never miss a new journey into the unknown. Now, let's step into the wake of an interstellar traveler. 3I Atlas first appears in the records as a faint, moving point that refuses to behave like a quiet stranger at the edge of the solar system. Survey telescopes sweep the sky as they always do, following patterns of motion and light that mark ordinary comets and asteroids. But this object does not fit cleanly into familiar categories. Its path hints at an origin beyond the distant comets that loop back again and again. The orbit is open, hyperbolic, a curve that does not close. From the very beginning, astronomers recognized that this visitor most likely comes from interstellar space, joining a very short list of known objects that pass through once and do not return. As more data accumulate, the strangeness deepens. Comets usually wake up as they move inward and sunlight grows stronger. Frozen material near the surface begins to sublimate, changing directly from solid to gas, and this escaping gas drags dust with it, building a hazy atmosphere called the coma and a tail that stretches away from the sun. 3I Atlas follows this script only in part. Observers reconstruct its earlier path using archive images taken months before the official discovery, and find hints that it is active, faintly shedding material at distances where most comets remain quiet. Activity so far from the sun is not entirely unknown, yet it is rare. Some long-period comets show distant outbursts when buried pockets of carbon monoxide or carbon dioxide begin to warm, but the behavior of 3I Atlas is stronger and more persistent than many of those cases. Its early brightness changes and extended coma suggest that energy is reaching volatile material through cracks, layers, or internal pathways that are not yet understood. In the weeks that follow, dedicated observers turn larger instruments toward the newcomer. Professional observatories and skilled amateurs alike track its rise in activity. Filtered images reveal an asymmetric coma and small jets of dust and gas that seem to change with time. The object rotates in roughly half a terrestrial day, so any active region on its surface repeatedly swings into sunlight, vents, and then cools again. The rotation period is not especially strange for a small, icy body, yet in combination with the complex jets, it suggests a nucleus that is not uniformly active. Instead, it appears patchy and restless, with regions that flare and regions that remain dark. Spectroscopic studies, which split the light into its component colors, add another layer. They show the signatures of water vapor and common cometary gases, but also an unexpectedly strong presence of metals, including nickel. Metal atoms and ions appear around many comets when dust grains are heated and broken apart. Yet the abundance near 3I Atlas seems enhanced compared with typical solar system comets. A halo rich in metallic dust and gas implies that the solid material itself is unusual, either in composition, structure, or both. Observers see a coma that is not only bright, but also chemically complex. The path of 3I Atlas through the inner system sharpens the sense that this is not a gentle, passing snowball. It rushes toward its closest point to the sun at tens of kilometers per second, threaded through a landscape already filled with interplanetary dust, solar wind, and magnetic fields. Even before that close approach, space weather instruments note that the environment around the object must be evolving quickly as solar storms sweep past it. Each burst of charged particles from the sun can strike the coma and tail, stripping electrons, bending the flow of dust and gas, and possibly triggering new activity on the surface. Against this background, one feature stands out in image after image. Alongside the more ordinary tail that stretches away from the sun, 3I Atlas displays a persistent structure that appears to point sunward, almost as if the comet is pushing back against the radiative pressure that normally sweeps material away. Sunward-pointing features have been seen on other comets as fine, curved streamers of dust or gas, created by particles that are heavy enough, slow enough, or electrically influenced enough to resist the outward push of sunlight. In 3I Atlas, this feature is unusually clear and persists both before and after its closest approach to the sun, implying that the underlying mechanism is stable over time rather than a brief flare. Astronomers discuss multiple explanations. Some focus on the size distribution of dust grains and the balance between gravity and light pressure. Others point to electromagnetic forces that can shape the flow of charged dust in ways that simple models of neutral gas cannot capture. No single explanation yet accounts for all of the observations, and that is where the sense of mystery begins to solidify. This is an interstellar object, carrying material formed around another star or in a different region of the early galaxy, now interacting with the environment near the sun under conditions that have rarely been studied in such detail. It does not behave in ways that are completely alien, yet the mix of familiar and unfamiliar behavior suggests that the solar system is being gently probed by something that remembers a different birthplace. Each new image, each brightness curve and spectrum adds a piece of information, but also raises a fresh question. When did this object leave its home system? How long has it traveled through interstellar space? What does its hyperbolic path and unusual activity tell researchers about the processes that shape small bodies between the stars? As 3I Atlas continues inward, steadily losing material and building an ever more extended halo of dust and gas, it becomes clear that the most important part of its story may not be the nucleus itself, but the enormous, evolving stream of debris that it leaves behind. The trail is not a thin line, but a widening volume, a kind of dusty corridor laid down along its trajectory. Within that corridor, grains of many sizes move at slightly different speeds and angles, some racing ahead, some lagging behind, some pushed aside by light and by the solar wind. Over time, this complex cloud begins to intersect the broad orbital paths of the planets, silently establishing future points of contact long after the solid visitor itself has passed outward and away. As 3I Atlas swings inward toward the sun, the point-like object that first appeared in survey data reveals itself as a machine of constant release, its surface venting material in complex patterns that blur the line between ordinary comet behavior and something more demanding to explain. Continuous monitoring shows that the nucleus is rotating roughly once every 15 to 16 hours, a spin that is fast enough to move active regions in and out of sunlight several times a day, but slow enough that jets have time to grow, twist, and disperse before the surface turns away again. Each rotation reshapes the coma, the hazy envelope of gas and dust surrounding the nucleus, and each rotation sends fresh material into space along slightly altered directions. In most comets, outflow tends to form a diffuse fan that gradually smooths out observational irregularities. But in this case, high-resolution images keep revealing distinct jets that persist on timescales longer than simple models would predict. Under standard assumptions, gas escaping from the sunlit side of a comet drags dust away from the surface, and the smallest grains are quickly pushed back by sunlight, forming a tail that points roughly away from the sun. The situation around 3I Atlas is more layered. There is indeed a tail driven outward by radiation pressure and the flow of the solar wind. Yet there is also a stubborn structure that appears to point toward the sun itself, a forward-leaning feature described by observers as a sunward-facing tail. This structure is present both before and after the comet's closest approach to the sun, which suggests that it is not a temporary disturbance, but a stable part of the object's interaction with its environment. Physicists know that heavy dust grains can resist the push of light longer than small ones, and that electric fields and magnetic fields can steer charged dust and gas along arcs that do not match a simple radial pattern. The material near 3I Atlas is not only neutral gas, it is a mixture of neutral particles, ions, and charged dust grains, all moving within the electromagnetic structure of the solar wind. The sun continuously emits charged particles that carry embedded magnetic fields, and as this flow encounters an active comet, it can stretch, kink, and fold the outflow into shapes that depend on both local conditions and the history of previous eruptions. 3I Atlas passes through phases when the solar wind is relatively calm, and phases when solar storms sweep past, bringing shocks and abrupt changes in pressure. Each such encounter has the potential to carve new patterns into the coma and tails. This complexity becomes particularly clear in data from a series of images taken with the Hubble Space Telescope over the course of late November and late December of the same year. In raw form, these images show a roughly circular coma surrounding a bright central condensation, with subtle hints of asymmetry that are easy to overlook. An astronomer experienced in image processing applies a mathematical filter designed to suppress circular, symmetric structures and enhance linear or curved features that break that symmetry. When the circular component is removed, the remaining image no longer looks like a simple, fuzzy sphere. Instead, sharp jets and streamers emerge, extending from the nucleus like narrow spokes. Comparing frames from late November to those from late December, the pattern of jets clearly changes. Early images show a dominant jet structure in one direction, while later images reveal a more balanced arrangement, with multiple jets of similar strength distributed around the nucleus. This is consistent with a rotational state in which several active regions take turns venting material, but it also hints at evolution in the underlying surface, where fractures may grow, new vents may open, and older ones may clog with refrozen material. The picture that emerges is of a nucleus that has been steadily reshaped by intense solar heating and by its own outgassing, so that by the time it moves past Earth's orbit, the pattern of release is broader and more nearly symmetric than it was on its way inward. Every jet feeds the growing debris corridor along the comet's track. Dust grains lifted by gas initially share the motion of the nucleus, traveling along almost the same path at tens of kilometers per second. But as soon as they leave the surface, other forces act on them. Solar radiation pressure pushes the smallest grains backward, stretching them into long tails. Larger grains respond more slowly and may drift only gently away from the original trajectory, building a thickened stream rather than a thin filament. Charged grains feel the influence of electric fields. Some are diverted sideways, some spiral along invisible magnetic lines, some slow down relative to the nucleus if their ejection direction opposes the main motion. Over many rotations, as the comet moves along its hyperbolic orbit, these many small deviations accumulate into a broad volume of dust, gas, and plasma. 3I Atlas becomes not only a compact nucleus in a visible coma, but also the moving center of an extensive, evolving medium that extends far beyond the region captured in a single telescope field. Amateur astronomers, using steadily improved cameras and software, contribute a flood of images that show this development in real time. Long exposure photographs reveal the rotation of jets as faint curls and asymmetric fans. Some report subtle changes in brightness that may be linked to outbursts when subsurface pockets of volatile material suddenly open to space. Others document the persistence of the sunward feature in different filters, suggesting that it contains both dust and gas components. Against this accumulation of evidence, the question shifts from whether 3I Atlas is unusual to how unusual it really is. Many of the observed behaviors have analogs in solar system comets, yet the combination of interstellar origin, enhanced metallic content, strong and persistent jets, and a stable sunward component that survives both before and after perihelion creates a situation that has rarely, if ever, been observed in this particular form. From the perspective of planetary science, the object offers a natural experiment in dust and plasma physics, under conditions that are difficult to reproduce artificially. From the perspective of those interested in broader cosmic patterns, the timing and geometry of its passage invite attention. The comet's fast swing around the Sun, its earlier close flyby of Mars, and its later approach to Jupiter all occur within a window when Earth, too, will pass near the densest portions of the debris field. The nucleus itself is on a one-time trajectory out of the solar system, unlikely to return on any human timescale, but the dust and gas it has released will maintain their own paths, shaped by gravity, sunlight, and electromagnetic forces. The jets imaged by space telescopes and ground-based observers are not only transient features, they are the sources of countless particles that will continue to move independently long after the central body has faded from direct view. As understanding of this process deepens, scientists begin to ask not only what the comet is doing now, but what its actions months ago and months hence will mean for the regions of space that Earth is destined to cross. The story of 3I Atlas unfolds against a long background of encounters between Earth and the debris of comets, a background that occasionally becomes dramatic enough to leave deep marks in historical memory. One of the clearest examples comes from the night in the early 19th century when the Leonid meteor stream produces a storm so intense that entire regions awaken to a sky filled with falling streaks. Observers in that year describe rates that climb into the hundreds of thousands of visible meteors over the course of an hour. A level of activity far beyond the familiar experience of modest showers that bring only a handful of shooting stars across the sky each night. Under such conditions, the distinction between individual events and a continuous phenomenon begins to blur. Instead of scattered traces, the sky appears covered with a dense pattern of luminous tracks, all seeming to originate from a region of the constellation Leo. Yet many witnesses note that a large fraction of the meteors seem to fall almost straight down. Modern analysis links this storm to the dust stream left behind by a periodic comet known today as Tempel-Tuttle. This comet loops around the Sun on a path that crosses the orbit of Earth, and over many returns it leaves behind trails of dense debris at slightly different longitudes along its orbit. When Earth passes through one of these particularly dense trails, the result is a Leonid storm. Calculations of orbital dynamics, dust ejection, and the gravitational influence of planets can reproduce the general timing and intensity of such storms. And the connection between Leonid activity and Tempel-Tuttle is now widely accepted. Yet even in this well-studied case, some observational details remain less neatly explained. Reports from the Great Storm describe meteors arriving from all directions, including paths that appear, to those under the sky, to descend vertically. In a standard meteor shower, the apparent paths of meteors radiate from a single point on the celestial sphere. Perspective means that overhead meteors can appear to fall nearly straight down, and this can account for many impressions. Still, reconstructions of the storm suggest that the geometry may have been unusual, perhaps involving a particularly compact filament of debris intersecting Earth almost head-on, or a local concentration produced by earlier dynamical effects in the stream. Some researchers have considered whether additional structures, such as a separate dust cloud or fragments from an earlier disruption, may have contributed to the most intense activity. None of these possibilities can be fully confirmed now, but together they illustrate a key fact. Even when a parent comet is known and the broad parameters of an orbit are well measured, the detailed spatial structure of a meteor stream can be complex, clumpy, and difficult to predict. This complexity is not confined to the Leonids. Each major meteor shower known today traces back to a parent body, often a familiar comet that has been observed over many passages. The Perseids, the Geminids, the Quadrantids, and many other showers are linked to specific cometary or asteroidal sources whose orbits are charted with precision. Earth intersects these streams at predictable times each year, leading to regular displays. However, the intensity of a given shower can vary greatly from one year to the next. Sometimes activity is low, with only a few visible meteors each hour. At other times, when Earth crosses a denser filament left by a recent passage of the parent body or shaped by gravitational resonances, the rate increases dramatically. These episodes show that meteor streams are not smooth rivers of dust, but intricate systems with waves, knots, and gaps. In this context, the Great Storm of the early 19th century stands as a reminder of what can happen when Earth encounters an especially dense region of debris. The atmosphere becomes, for a short time, a target for an enormous flux of small particles, each converting kinetic energy into light and heat high above the ground. The surface remains largely unaffected, but the human response is intense, and the event becomes part of the cultural record. For those studying current and future encounters with dust, storms like that act as natural laboratories preserved in historical accounts. They show what is possible when conditions align, and they expose gaps in theoretical understanding that persist despite decades of further research. As scientists now examine the trail of 3I Atlas, they draw on this history. The interstellar object, like Temple Tuttle, leaves behind a stream of debris along its path, but there are crucial differences. Temple Tuttle returns periodically, refreshing its stream and allowing detailed modeling over many orbits. 3I Atlas, by contrast, passes through the solar system once, on a hyperbolic path that carries it away and does not bring it back. The dust it releases inherits the high velocity of the parent body, and the initial conditions of the stream differ from those of ordinary periodic comets. Some of the material is ejected in directions that slightly slow its motion relative to the Sun. Some is launched sideways, creating components of velocity that spread the stream out of the original orbital plane. Some is likely to remain on hyperbolic paths and escape entirely, while other grains may be slowed enough to become bound to the solar system in new orbits. The result is a three-dimensional structure that will continue to evolve under the influence of gravity, radiation pressure, and electromagnetic forces long after the nucleus has left. When Earth moves through any portion of this structure, the interaction may be subtle or obvious. On the subtle end, the encounter might manifest only as a small increase in the background flux of micrometer-sized particles, too faint to produce easily visible meteors, but potentially detectable with sensitive instruments. On the more dramatic end, if Earth were to intersect a region of enhanced density, there could be a spike in visible meteors or even a storm, though that outcome would require conditions that are not currently favored by cautious modeling. Between these extremes lies a wide range of possibilities, many of which have not yet been fully quantified because the detailed distribution of dust in the 3I Atlas trail is unknown. This uncertainty links the current situation to the puzzles still surrounding historical storms. In both cases, the broad outlines are understood, but the fine structure remains enigmatic. The night of intense Leonid activity demonstrates that an apparently thin stream can contain concentrated filaments capable of producing extraordinary effects when crossed by Earth. The present passage of an interstellar object shows that the solar system occasionally receives debris streams that are not only structurally complex, but also compositionally distinct. Combined, these lessons hint that future encounters with the remnants of 3I Atlas may reveal behaviors that current models do not fully anticipate. The question is not simply whether a spectacular meteor storm will occur. It is also how the dust environment near Earth will change during and after the crossing, and what new data about dust dynamics, atmospheric interaction, and interplanetary structure might emerge from careful observation, whether the visible display is modest or intense. The debris of 3I Atlas does not disperse into emptiness in a simple, smooth way. Instead, as the weeks pass after perihelion, the volume of space it has disturbed becomes layered with dust grains of many sizes and compositions, each following a path set by the balance of forces acting upon it. When material first leaves the nucleus, it carries almost exactly the same velocity as the parent body, racing along a hyperbolic trajectory at tens of kilometers per second. At that moment, the grains are, in a sense, still part of the comet. Only after they have moved some distance away do the other influences begin to separate their destinies. Gravity from the sun continues to pull on them, trying to keep them on paths similar to that of the nucleus. Sunlight pushes outward on their surfaces, a radiative pressure that is especially effective on the smallest grains, which present a relatively large area compared with their mass. Charged particles from the solar wind sweep through the region, carrying magnetic fields that can couple to electrically charged dust and bend its motion in ways that have no counterpart in the behavior of neutral gas. In ordinary comet tails, these effects collectively sort grains by size. Fine dust is borne away quickly, forming long, faint tails that point away from the sun. Larger grains lag behind and remain closer to the original trajectory, creating a thicker, more persistent trail. In the case of 3I Atlas, the sorting process becomes more intricate because the initial velocities are high, the composition is unusual, and the pattern of jets creates strong components of motion that are not confined to a single direction. Grains ejected roughly along the direction of travel continue outward on hyperbolic paths, some eventually leaving the solar system entirely. Grains launched sideways drift into orbits that carry them above and below the original plane, widening the corridor of debris into a three-dimensional band. Grains expelled in directions that oppose the motion of the nucleus can be slowed significantly. Some of these may lose enough speed to become gravitationally bound to the sun, no longer following the hyperbolic escape route, but instead settling into elongated, or even, in rare cases, roughly circular orbits. This possibility arises from the basic mechanics of motion under gravity. If the ejection gives a grain a velocity vector that reduces its total energy with respect to the sun below the escape threshold, that grain can be captured. Whether this happens often in practice depends on the strength and geometry of the jets, the rotation of the nucleus, and the sizes of the grains. The sample script emphasizes that this is an open question, not a firmly established outcome. Still, even a small fraction of captured grains could make a difference, because the total number of particles released over months of activity is extremely large. Over longer timescales, another effect becomes important. This is the slow loss of orbital energy by dust grains due to the combined action of sunlight and the motion of the grain itself, often referred to in technical work as the Poynting-Robertson effect. A grain orbiting the sun absorbs light and re-emits it, and because of the way this process interacts with its direction of motion, there is a tiny drag that causes the orbit to shrink. Very small grains, which feel radiation pressure strongly, are often pushed outward or blown away before this drag can act for long. But larger grains, which feel radiation pressure less strongly, can spiral gradually inward over thousands to millions of years. In this way, dust released by comets and asteroids can form a background distribution that fills the inner solar system, drifting sunward while also being stirred by planetary gravity. This drifting dust helps create the zodiacal light, the faint glow that can be seen from dark locations as a softly brightened band along the plane of the planets after sunset or before sunrise. It also contributes to tenuous clouds of material near planets and their moons. Saturn's rings, though dominated by larger icy particles, are accompanied by extensive dust structures that persist over long periods. Observations near Earth have revealed regions of enhanced dust density associated with gravitational balance points in the Earth-Moon system. These are sometimes referred to as Kordylewski clouds, after the astronomer who first proposed their existence. They are difficult to detect, but independent groups across decades have reported signs that such electrostatically influenced dust concentrations exist. The behavior of 3I Atlas sits within this broader framework, but alters the initial conditions. Spectral analyses indicate that the coma of this interstellar object contains an unusually high abundance of nickel and other metals compared with many well-studied solar system comets. If the dust grains are correspondingly metal-rich, they will have different densities, conductivities, and magnetic susceptibilities than predominantly silicate or icy grains. Denser grains respond differently to radiation pressure, tending to be pushed outward less efficiently. Conductive grains can accumulate charge more readily when exposed to strong ultraviolet light from the sun, building up electric potentials of hundreds or even thousands of volts relative to their surroundings.
Once charged, these grains interact strongly with the plasma environment. They can attract or repel other charged grains, stick together into loose aggregates, and respond to electric fields and magnetic fields in ways that cause them to cluster rather than disperse. Laboratory experiments on dusty plasmas and observations of planetary rings suggest that under some conditions, such charged grains can form filamentary or clumped structures, sometimes referred to as electrostatic bundles. In these structures, the mutual electric forces between grains and the surrounding plasma help maintain coherence over distances much larger than the size of individual particles. If similar processes occur in the debris stream of 3I Atlas, the resulting structure may not resemble a smooth cloud. Instead of thinning evenly, parts of the trail could condense into denser knots, sheets, or filaments of dusty plasma. Some of these might drift along roughly with the average motion of the stream, while others could be slowed or deflected by interactions with the solar wind and the magnetic field carried within it. Over time, gravitational perturbations from planets, especially giant ones like Jupiter, would further stir and reshape these features. The sample script raises the possibility that Earth might encounter not just a uniform increase in dust, but one or more of these concentrated structures during the months when the orbit of our planet crosses the region where the densest part of the stream is expected to lie. This is speculative because the detailed mapping of such structures is far beyond current observational capabilities, yet it is grounded in known physics of dusty plasmas and in the observed complexity of other dust environments in the solar system. Even without invoking strongly clumped structures, the combination of high metallic content, high initial velocities, and varied ejection directions already implies that the 3I Atlas stream will contribute a distinct component to the inner system dust population. Some grains will be lost to interstellar space, carrying with them a record of their brief passage near the Sun. Some will spiral inward, joining the existing zodiacal dust and gradually altering its composition. Some may become trapped in resonant orbits with planets, forming subtle enhancements along certain paths. Others may interact with pre-existing dust clouds, such as the faint concentrations near the Earth-Moon system, adding new material to these already complex regions. From the perspective of a scientific documentary, the picture that emerges is not of a single dramatic event, but of a slow building of an extended dust ocean, a medium filled with grains whose origins trace back to another star system. This ocean is invisible to ordinary sight, except where it is illuminated as meteors or as faint scattered light. Yet it is real and dynamic. Within it, 3I Atlas has carved a fresh corridor, rich in metal-bearing dust, and structured by jets, radiation, gravity, and plasma processes. The question that now begins to take shape is how the geometry of this corridor aligns with the orbit of Earth, and what subtle or obvious effects may arise as our planet moves through regions that were, only months before, swept by the turbulent outflow of an interstellar visitor. The path of 3I Atlas through the inner solar system is not just a line drawn on a chart. It is a moving frame of reference against which the orbit of Earth slowly advances, and the places where these paths approach one another are set years in advance by gravity alone. The interstellar object rushes inward on its hyperbolic course, brushes past Mars in early October, sweeps through its closest approach to the Sun in late September, and then climbs outward again, crossing the orbital distance of Earth and later approaching the domain of Jupiter. During this sequence, the nucleus itself never comes especially close to our planet. Yet the material it has released spreads out along and around its route, forming a corridor of dust and plasma that does occupy regions Earth will later traverse. Orbital integrators, the numerical tools that track the motion of bodies under gravity, show that by the time Earth reaches the relevant sectors of its own path, the solid core of 3I Atlas is already beyond our orbit and still moving outward at high speed. But its debris is not confined to a single compact knot near the nucleus. Dust grains pushed backward by radiation pressure, deflected sideways by jets, or slowed by ejection against the direction of motion, linger behind and alongside the path of the source. Grains that remain gravitationally bound to the Sun follow their own individual orbits, close to the hyperbolic track at first, but gradually diverging. The geometry of a crossing is defined by this interplay between the simple, predictable path of Earth and the more complex, evolving structure of the stream.
Earth travels around the Sun in a nearly circular orbit at about 30 kilometers per second. 3I Atlas, near perihelion, moves at more than twice that speed.
When it passes the orbital radius of Earth, the relative velocity between the two bodies is large, but the physical separation in space at that moment is sufficient to prevent any close encounter. Instead, the key regions are those where, some months later, Earth finds itself in the same broad volume that the comet and its debris previously occupied. In the sample script, attention focuses on March and April as the interval when Earth moves into the zone populated by material that was ejected at lower speeds or in directions that reduce its heliocentric energy. These grains, having been launched with components of velocity that oppose the main outward motion, have slowed relative to the nucleus itself. They lag behind along the path, occupy neighboring regions of the orbital plane, or drift slightly inward toward the Sun under the slow drag of the Poynting-Robertson effect. When Earth arrives, it does not meet the nucleus, but instead crosses a region where such grains are more likely to be present than in the undisturbed background of interplanetary dust. Visualizing this crossing requires stepping back from the familiar two-dimensional diagrams of orbits. In those diagrams, lines represent idealized paths in a plane, and intersections look sharp and simple. In reality, both the orbit of Earth and the trail of 3I Atlas occupy finite volumes around those lines. The orbit of Earth is surrounded by its own extended environment, including the magnetosphere, the exosphere, and low-density dust structures. The trail of the comet is not infinitely thin. It has a width, thickness, and internal structure. The question then becomes not whether the lines intersect, but how deeply Earth's extended environment penetrates the extended corridor of debris, and in what part of that corridor the penetration occurs. If Earth passes only through the dilute outer regions of the stream, the effect may be limited to a modest increase in the flux of small particles entering the atmosphere, perhaps detectable as a slight enhancement in sporadic meteors or satellite drag, but not dramatic to ordinary observers. If, by contrast, the crossing intersects a denser filament, especially one that has been created or focused by earlier gravitational interactions, the encounter could be sharper. In that case, the geometry would resemble, on a smaller scale, the conditions that produced historical meteor storms, in which Earth briefly cuts through a compact concentration of dust. The likelihood of such an alignment is difficult to assess with confidence, because the fine structure of the 3I Atlas stream is unknown, and might remain unknown until after the crossing, when observational data can be analyzed. A further complication arises from the inclination and orientation of the comet's trajectory relative to the ecliptic, the plane in which most planets orbit. 3I Atlas approaches on a path that is not perfectly aligned with this plane. Its inclination means that as it rushes inward and outward, it passes above and below the main planetary disk. Dust ejected from the nucleus inherits this vertical component and spreads into a band that may sit at a slight angle to Earth's orbit. Over time, gravitational perturbations tend to pull dust toward the ecliptic, but this process takes longer than the months separating the passage of the comet from the earlier part of the Earth crossing. As a result, the densest part of the band in March and April may lie slightly displaced relative to the orbital plane of Earth, and the actual intersection may occur with an offset. Even a modest vertical separation can significantly change the number of grains that encounter Earth's extended atmosphere. Modelers attempt to estimate these effects by running ensembles of numerical particles, releasing them from a simulated nucleus with a range of speeds and directions consistent with observed jets, then letting them evolve under the gravitational pull of the Sun and planets, radiation pressure, and approximate drag from sunlight. These simulations can predict general patterns, such as the expected locations of thicker or thinner regions along the path, but they are sensitive to assumptions about the strength and geometry of the jets, and about the size distribution and composition of the grains. The sample script underscores that the data on these inputs are limited, especially for an interstellar object whose internal structure and volatile inventory are not directly accessible. The result is that predictions about March and April carry substantial uncertainties and must be framed as ranges of possibilities rather than precise forecasts. What can be said with some confidence is that by the time Earth moves through the relevant sectors of its orbit, the debris from 3I Atlas will have spread enough that the crossing will not be a singular, sharp moment. Instead, it is likely to be an extended season, spanning weeks to perhaps a couple of months, during which the local dust environment around Earth slowly changes. Within this window, there may be days or nights when the flux of particles is somewhat higher, perhaps due to partial alignment with a denser filament, and other times when it is closer to background levels. The duration of the potential interaction means that any cumulative effects on the upper atmosphere, on satellite drag, or on subtle electromagnetic conditions could arise gradually rather than as an abrupt spike.
From a documentary perspective, the sense of approach comes not only from orbital diagrams, but also from the calendar. Investigators know that the geometry is fixed. The orbits of Earth and 3I Atlas were determined by gravitational dynamics long before the comet was even discovered. The streaming of dust along the hyperbolic path, the slowing of some grains, and the scattering of others have been underway for many months. As late winter turns towards spring in the northern hemisphere, Earth slides into the coordinates where modeled particles from the comet are expected to reside. Night by night, the sky appears the same to casual observation, yet instruments capable of counting meteors, measuring atmospheric ionization, and tracking small changes in satellite orbits may begin to detect patterns that deviate from long-term averages. In this way, a purely geometric situation, defined by intersecting paths in three-dimensional space, translates into a lived interval of time on Earth. A period in March and April when the planet is effectively sampling the wake of an interstellar visitor. The fact that this sampling occurs around the March equinox adds another layer of context. At this time of year, the geometry between Earth, Sun, and the orbital plane favors the visibility of the zodiacal light after dusk and before dawn. Observers under dark skies already see more clearly the diffuse glow of interplanetary dust. Any subtle changes in the brightness or distribution of this glow, caused by additional dust along the line of sight, would be easiest to detect during such a season. The coincidence is not necessarily causal, but it means that conditions for noticing changes in the dust environment are naturally better at the same time when the calculated crossing takes place. Thus, by the time the calendar reaches March, the abstract curves traced on orbital plots resolve into a more immediate feeling. Earth is drawing into a region where the space between planets has been freshly filled with material from a body that does not belong to this system, and the outcome of that passage remains open, constrained by physics, yet not fully mapped. Jupiter waits further out in its broad orbit, a massive presence whose gravity shapes the architecture of the solar system on scales that dwarf the path of any single comet. As 3I Atlas recedes from the Sun after perihelion, its trajectory carries it toward a point where it comes relatively close to this giant planet. Not close enough for a direct encounter, yet near enough that questions about gravitational influence and subtle effects naturally arise. Calculations of the orbit show that around the middle of March, the distance between 3I Atlas and Jupiter shrinks to a value comparable to a fraction of the region where Jupiter's gravity dominates over that of the Sun. A zone that planetologists often describe in terms of the planet's sphere of influence. This zone, sometimes defined more precisely as the Hill region, marks the approximate boundary within which a small object can remain stably bound to the planet rather than to the Sun, provided its speed and direction fall within the right range. In the case of 3I Atlas, the closest approach lies outside this core gravitational region, at a separation on the order of 1/5 of an astronomical unit. Yet, that distance is still small on the scale of planetary orbits. It is close enough that the diffuse dust and plasma following the comet's path will pass through a changing gravitational landscape, one shaped not only by Jupiter itself, but also by its many moons. Jupiter hosts a complex family of satellites. The large Galilean moons circle relatively close in, following nearly circular orbits near the planet's equatorial plane. Further out, dozens of irregular moons move along elongated, inclined, and often retrograde paths, some grouped into dynamical families that likely share a common origin in past capture or disruption events. When 3I Atlas passes by, it does not thread between these moons, yet the debris surrounding it flows through a space where their collective gravitational signatures blend into that of the planet. One of these irregular satellites, whose name in Greek mythology relates to praise and favorable omens, draws attention in theoretical discussions because its orbit happens to bring it closer in orbital phase to the path of 3I Atlas than most others. This proximity does not mean a collision or a close flyby in the usual dramatic sense, but it does raise the possibility that some fraction of the dust, especially grains whose velocities are already slightly slowed by ejection geometry, could be perturbed into new orbits that resonate with Jupiter's motion. The physics of such an interaction is subtle. The nucleus of 3I Atlas moves fast, carrying most of the system's kinetic energy. Its own trajectory is only gently deflected by Jupiter's gravity at the distances involved. The dust and gas, however, travel more slowly relative to the planet and can be more easily influenced. Gravitational focusing, a process in which a massive body slightly bends the paths of passing particles, can concentrate dust in the downstream direction, creating regions of enhanced density in the wake of the planet. If part of the comet's debris stream passes near Jupiter, this focusing could gather some of the grains into thin, curved sheets, or into trails that follow or precede the planet in its orbit. Over time, these structures might smear out, but for a period, they could exist as real, if faint, enhancements in the surrounding dust population. There is also the possibility of partial capture. A dust grain passing close to Jupiter, with the right combination of speed and direction, can lose enough energy relative to the planet that it becomes temporarily or permanently bound. In the case of 3I Atlas, most grains are unlikely to meet the exact conditions required, given the high overall relative velocity. But even a tiny fraction finding stable orbits would mean that some material from an interstellar object becomes incorporated into the Jovian system. Those grains could join existing dust populations, such as the tenuous rings of Jupiter, or the diffuse envelopes surrounding some of its moons. Over much longer spans of time, they might be swept into the planet's upper atmosphere, becoming part of the cloud decks that are visible through telescopes as bands and spots. Beyond gravity, Jupiter's magnetic and plasma environment adds further complexity. The planet's rapid rotation and internal dynamo generate a strong magnetic field, which traps charged particles in vast radiation belts. Volcanic activity on the moon Io supplies a continuous source of plasma, which is then distributed along magnetic field lines to form a torus of ionized gas encircling the planet. Dust grains entering this environment and acquiring electric charge through sunlight and plasma impacts experience forces from both the gravitational and electromagnetic fields. In principle, some of the charged dust released by 3I Atlas and steered toward Jupiter's neighborhood could be drawn into these structures, adding an interstellar contribution to clouds that are already influenced by the interaction of moons, plasma, and magnetic fields. The actual magnitude of such an effect is uncertain and likely small compared with the pre-existing Jovian environment. But its possibility illustrates how a single passing object can connect distant regions of the solar system. The timing of the close passage resonates in another way. As 3I Atlas moves outward past the orbit of Earth, its closest approach to Jupiter occurs in the same general month when Earth itself is beginning to cross the inner part of the debris corridor. In the language of orbital dynamics, this means that Earth and Jupiter are both in geometrical configurations that intersect different portions of the same broadened stream. One planet samples the inner, sunward drifting grains near 1 astronomical unit. The other dwells further out, near 5 astronomical units, where the hyperbolic trajectory of the nucleus curves past. The two planets are not aligned in a straight line with the Sun and the comet, yet their simultaneous engagement with different regions of the same interstellar trail suggests a kind of large-scale resonance, not mystical but geometric, in which the giant planet and the inhabited world both interact with material from beyond the solar system within the span of a few weeks. In the sample script, this coincidence invites reflection on archetypal patterns and mythic associations, especially in connection with the irregular moon, whose name evokes favorable omens. In scientific terms, such naming is purely historical, a product of human choices. Yet, the overlap of names, motions, and observational opportunities is striking enough to draw speculative attention. An interstellar object, carrying a composition distinct from typical Jupiter family comets, passes near a planet long associated with rulership and expansion in cultural traditions, while at roughly the same time, the dust it has shed begins to brush the environment of Earth. Researchers who hold a more symbolic perspective see in this pattern a kind of cosmic alignment, whereas dynamicists view it as a natural but interesting result of the way that high-inclination, high-speed orbits intersect the established planetary architecture. Both perspectives agree on one point. This is a rare configuration, and it offers a unique chance to study how an interstellar visitor interacts with both the inner and outer domains of a planetary system in a single passage. A further layer emerges when considering resonances, the repeating gravitational relationships between orbits that can stabilize or destabilize motion over long times. Dust grains, perturbed by Jupiter during the passage of 3I Atlas, could find themselves in orbits whose periods bear simple ratios to that of the planet. In such resonant configurations, repeated gravitational nudges at the same orbital phase can either pump up or damp down eccentricities and inclinations. Over many cycles, this can corral dust into arcs or gaps, similar to the way resonances with Saturn shape structures in its rings, or how resonant relationships with Jupiter sculpt the distribution of asteroids in the main belt. The initial amount of cometary dust interacting with Jupiter during this encounter may be modest, but the principle remains. Each grain that enters into a resonant relationship becomes part of a long-term pattern that can outlast the brief visibility of the parent body. In thinking about these processes, scientists are constrained by the limits of observation. Direct imaging of dust near Jupiter at the relevant scales is challenging. Instrumental sensitivity, background light, and the sheer distance involved make it difficult to trace fine structures in situ. Instead, researchers rely on a mixture of remote sensing, in situ measurements from past missions, and numerical models. Spacecraft that have flown past Jupiter, such as Galileo and Juno, have provided detailed information about the planet's magnetic field, plasma environment, and cloud patterns, but none were in the right place at the right time to sample the specific debris of 3I Atlas. Future missions may pass through regions where remnants of this interstellar material have been incorporated, but by then, the grains will be indistinguishable from other dust on the basis of their immediate behavior alone. Their origin will be implied, rather than directly tagged. For now, Jupiter's role in the story of 3I Atlas remains that of a distant but significant actor. Its gravity and magnetic field stand ready to deflect, focus, or absorb portions of the debris stream, while its many moons continue their own intricate dances within this framework. The close passage in March does not threaten dramatic upheaval, yet it offers a quiet, large-scale experiment in how a massive planet responds to the passage of a fast, dusty visitor from another star. At the same time, back in the inner system, Earth moves steadily toward its own encounter with the stream. In this way, the narrative stretches from the Jovian realm to the terrestrial, linking distant influences with local conditions and setting the stage for the next questions. How charged grains behave near Earth, how subtle dust clouds form and dissolve around our planet and its moon, and how these invisible structures might shift under the influence of an interstellar dust storm passing through the neighborhood of the Sun. Around Earth, the space that appears empty to casual thought is in fact filled with a changing mixture of gas, plasma, and dust. And the arrival of debris from 3I Atlas will enter into this already complex environment rather than into a clean vacuum. Dust grains released by the interstellar object and drifting into the inner solar system move through sunlight that constantly charges their surfaces. Ultraviolet photons knock electrons free from the grains, leaving them with a net positive charge when they are in full light. In darkness, on the night side of an orbit, or within shadows, the balance shifts and incident electrons from the surrounding plasma can accumulate, driving the potential in a more negative direction. Each grain, therefore, does not carry a fixed charge, but an evolving one, responding to illumination, shadow, and the density of nearby electrons and ions. For metal-rich grains, such as those inferred from spectroscopic observations of the 3I Atlas coma, this charging can be particularly efficient. Conducted material allows charges to redistribute quickly across the surface, and the resulting electric fields between grains can become strong on microscopic scales. When a population of such grains shares a region of space, electrostatic forces begin to matter. Grains with opposite charges attract, forming loose aggregates. Grains with like charges repel, unless the surrounding plasma neutralizes the interaction. As they cluster, they create larger structures that have their own charge distributions and respond differently to external fields than single particles do. Laboratory experiments in plasma chambers show that under appropriate conditions, dust grains suspended in ionized gas can organize into filaments, layers, or clumps, sometimes called dusty plasma crystals or clouds. In these systems, the grain population behaves collectively, supporting waves and oscillations rather than acting as independent particles. Translated to the scale of interplanetary space, similar physics implies that dust from 3I Atlas may not simply spread uniformly through the regions it enters. Instead, in some locations, especially where the background plasma environment fosters charge separation, it could form transient but coherent swarms, electrostatic bundles in which grains remain correlated over distances far larger than their individual sizes. Near Earth, additional factors shape the behavior of charged dust. The planet's magnetic field carves out a cavity in the solar wind, deflecting most of the incoming charged particles and trapping some in belts that encircle the planet. These belts, together with currents flowing in the upper atmosphere and in the magnetosphere, form a structured electromagnetic environment with regions of enhanced and reduced field strength. Charged dust grains entering this environment experience forces proportional to their charge and velocity, which can bend their trajectories into spirals around magnetic field lines or guide them along those lines toward the polar regions. The degree to which this happens depends on the size and mass of the grains. Very small particles, with sizes comparable to those of smoke, are strongly influenced and can be swept into complex paths. Larger grains, more like sand in scale, are dominated by gravity and inertia, with electromagnetic forces acting as subtle perturbations. The spectrum of grain sizes released by 3I Atlas almost certainly spans this entire range, so the resulting motions around Earth will be varied. Some grains will behave almost like neutral meteoroids, entering the atmosphere on near straight lines and producing faint streaks of light.
Others may drift for long periods on trapped or semi-trapped trajectories, inhabiting regions of near-Earth space that are already busy with artificial satellites. The concept of elusive dust clouds near Earth is not entirely theoretical. Observations stretching back decades have suggested that at the leading and trailing gravitational balance points of the Earth-Moon system, the 4th and 5th Lagrange regions, there are faint concentrations of dust. These so-called Kordylewski clouds are difficult to image because they are extremely diffuse and because scattered light from the Sun and Earth can overwhelm the signal. Nonetheless, several independent efforts have reported excess brightness or polarized light consistent with clouds of fine particles lingering in these regions. The interpretation remains debated, but the idea that electrostatically influenced dust can accumulate near gravitationally stable points has become part of the broader picture of near-Earth space. If the trail of 3I Atlas contributes additional charged grains to the Earth-Moon system, some fraction of that material could be captured into, or at least spend extended periods passing through, these balance zones. In that case, the interstellar dust would not simply sweep past once, but could become incorporated into semi-persistent, shifting clouds that share the orbital rhythm of the Earth-Moon pair. Beyond the Lagrange regions, Earth's broader dust environment includes the tenuous veil of particles that give rise to the zodiacal light and the more local distributions that intersect with satellite orbits. In low Earth orbit, where many satellites and fragments of space debris circle the planet, the presence of additional dust may modestly increase drag or collision probabilities. Most grains from 3I Atlas are likely to be too small to be immediately hazardous to large structures, but in aggregate, an increase in the flux of high-speed particles can alter the plasma sheath around spacecraft, affect surface charging, and contribute to erosion of exposed materials. Particularly dense clumps of dust, if they exist and if Earth crosses them, could temporarily push conditions closer to those experienced during strong solar storms, when increased atmospheric heating and expansion raise drag on satellites and accelerate orbital decay. In more extreme speculative scenarios, if a sudden enhancement of metallic dust were to intersect the populous regions of orbital space, the risk of small impacts might rise enough to trigger a cascade of fragmentations, a chain reaction sometimes referred to as a debris syndrome. The sample script highlights this as a possibility rather than a prediction. Quantitative assessments suggest that the most likely outcome is more modest, mild increases in drag, and a higher background of small impacts, detectable by sensitive instruments but not necessarily catastrophic. Still, the mechanisms by which charged dust interacts with electromagnetic fields and existing debris remain important to understand, because they govern how the environment around Earth responds to any external influx, whether from interstellar objects, ordinary comets, or changes in solar activity. At higher altitudes, near and beyond the geostationary belt, charged dust interacts more directly with the outer magnetosphere. Here, the balance between gravitational and electromagnetic forces shifts further toward the latter for small grains. Some particles may be accelerated along field lines toward the polar caps, where they can deposit energy and material into the upper atmosphere. Others may find themselves in drifting orbits that encircle Earth on timescales of days to weeks, gradually losing energy through interactions with plasma waves. From the ground, such processes are nearly invisible, yet they can leave signatures in careful measurements of atmospheric ionization, radio wave propagation, and subtle variations in auroral activity. When dust from 3I Atlas arrives, it will enter this network of processes. Electrons stripped from the grains or knocked off by sunlight will join existing populations in the ionosphere and magnetosphere. Grain impacts on the upper atmosphere will contribute to a continual rain of material that already includes particles from asteroids, comets, and interstellar space. The difference lies in composition and timing. If, as observations suggest, the 3I Atlas dust is enriched in nickel and other metals, the chemical traces it leaves in the atmosphere and in collected samples could stand out from the usual background. Over time, some of this material will settle through the atmosphere and deposit on the surface, joining the thin layer of cosmic dust that accumulates across the planet. In principle, careful analysis of micrometeorite collections might one day reveal a layer with distinctive composition corresponding to the passage of this interstellar stream, though distinguishing it from other sources will be challenging. In considering all these possibilities, a key point remains. Charged dust does not simply act as a passive contaminant. It participates in the electromagnetic life of near-Earth space. The arrival of new dust from 3I Atlas, especially if it includes electrostatic bundles or plasmoid-like structures as suggested in the sample script, could transiently reorganize currents, fields, and particle populations in ways that are not yet fully captured by models. The resulting changes might be subtle and distributed, rather than dramatic and obvious. But they would still represent a real coupling between an interstellar object and the delicate layers of plasma and dust that surround our world. The material released by 3I Atlas carries information not only in its motion, but also in its chemistry, a record of formation and alteration under conditions that did not belong to the early solar system. Spectroscopic observations during its passage near the Sun reveal familiar signatures of water vapor and the breakdown products of common cometary gases. Yet they also show unusually strong lines from metals such as nickel. Metals in cometary comae are not new to science. Many comets release sodium, iron, and nickel atoms when dust grains are heated or fractured. What stands out in the case of this interstellar object is the relative strength of those metal signatures compared with the usual volatile species. This suggests that the dust it ejects may be richer in metal-bearing minerals than the average for local comets. Water is still present, indicating that ice plays a role in driving activity, but the mixture of ices and rock appears skewed toward denser, more metallic phases. This composition matters because it influences how the grains respond to radiation, gravity, and electromagnetic forces, but it also matters because it hints at the conditions in the environment where the object originally formed. Metal-rich grains condense in regions where temperatures and pressures favor the formation of refractory compounds, and the presence of volatile ices alongside them implies that the parent body assembled from material that experienced a wide range of conditions before being locked into a single mass. In the solar system, such mixtures are seen in some meteorites, where metal and silicate phases sit alongside complex organic molecules. It is therefore reasonable to consider that the dust of 3I Atlas might also carry organic compounds, even if current observations cannot yet specify which ones. In ordinary comets, spectral studies reveal cyanide radicals, simple hydrocarbons, and molecules containing combinations of carbon, nitrogen, oxygen, and hydrogen. Laboratory analyses of collected interplanetary dust particles show amino acids and other complex organics, some with isotopic ratios that point to interstellar origins. These findings support a broader picture in which small bodies act as carriers of prebiotic chemistry, delivering molecular building blocks to planetary surfaces over long spans of time. The interstellar nature of 3I Atlas invites the extension of that picture beyond a single planetary system. If its nucleus formed in a distant region of the galaxy, perhaps around another star, then the ices and dust grains it contains record the chemistry of that environment. The enhanced metallic content observed in its coma may be only one aspect of that record. Within the released dust, there could be organics that differ in detail from those commonly seen in local comets, whether in their structure, their isotopic signatures, or their associations with other minerals. At present, these possibilities remain largely speculative because no direct samples of the dust have been captured. Observational spectra integrate light from large volumes, and subtle features can blend or fall below detection thresholds. Nevertheless, the combination of water, metals, and faint ultraviolet structures consistent with dust jets indicates that the material is diverse and that at least some grains are finely divided, increasing their surface area and reactivity. Historically, episodes when Earth passes through the debris of comets have sometimes coincided with significant changes in climate or in the spread of disease.
Long after
One
the
such
earliest
period, during the
experiments
middle of the
life
14th
have
century,
settled into
has
calmer
prompted
rhythms, the
investigations into whether
Silurian
dust from a passing comet might have played a role in the conditions surrounding a major pandemic. Some researchers have suggested that fine dust particles entering the atmosphere could have altered weather patterns, affected cloud formation, or carried unusual chemical or biological agents. Others argue that terrestrial factors, including human movement and pre-existing pathogens, suffice to explain the observed spread. The evidence is fragmentary, and no consensus has emerged that firmly links that historical outbreak to a specific dust stream. Still, the discussion underscores a point. When Earth moves through a dense region of cometary debris, the encounter is not purely visual. Along with meteors, unseen particles can interact with the atmosphere, depositing energy and material in ways that might have subtle but real effects. In the case of 3I Atlas, the sample script notes that cyanide-bearing compounds appear in its spectrum, much as they do in many comets. Cyanide is a simple yet reactive molecule, capable of both toxic and constructive roles in chemistry. In planetary atmospheres, cyanide and related species can participate in pathways that lead to more complex organics. In laboratory settings, reactions involving cyanide have been used to synthesize amino acids and nucleobase precursors under conditions meant to mimic primordial environments. If dust and gas from an interstellar comet rich in such compounds were to be injected into the upper layers of a planetary atmosphere, the result would not necessarily be a direct hazard, especially given the small quantities involved relative to the mass of the atmosphere.
But it could add a transient pulse of reactive material to chemical cycles that already operate there. The same is true for metal vapors. As dust grains from 3I Atlas ablate in the upper atmosphere, they release atoms of nickel, iron, and other metals into regions where they can act as catalysts or condensation nuclei. Even now, Earth's atmosphere hosts layers of metallic atoms and ions derived from ordinary meteoroid ablation, and these layers are known to influence ionospheric chemistry and noctilucent cloud formation. The arrival of an interstellar dust stream that is richer in metals could temporarily enhance such layers, perhaps altering the brightness or frequency of certain high-altitude cloud phenomena, or slightly modifying the efficiency of charge transfer processes in the mesosphere and lower thermosphere. Again, the scale of these changes is likely modest, yet they represent a direct chemical coupling between the dust composition of a passing object and atmospheric behavior. Beyond Earth, the chemistry of 3I Atlas also concerns environments such as the Jovian system and the interplanetary medium itself. Grains that are captured into orbits around the Sun, whether by slowing due to ejection geometry or by later interactions, will over time become part of the general dust population. As they spiral inward under the slow drag of sunlight, their material will be exposed to repeated cycles of heating and cooling, ultraviolet irradiation, and interaction with the solar wind. Complex molecules can be both destroyed and created in these conditions. Some organics may break apart, while others may form coatings on grain surfaces, changing their optical properties and reactivity. In the denser regions of the zodiacal cloud, collisions between grains can produce fresh surfaces and fragments, renewing the supply of chemical sites. In this sense, the entry of 3I Atlas material into the inner solar system is not a one-time event, but the beginning of a longer-term contribution to the chemical evolution of interplanetary space. For astrobiology, the arrival of an interstellar dust stream offers a natural experiment in panspermia-related ideas, though strict claims must be stated carefully. The concept that life, or its precursors, can transfer between star systems on dust grains or small bodies has long been proposed. Microorganisms or complex organic molecules might survive prolonged exposure to space if shielded within rocky fragments or icy mantles. In reality, the harsh environment of interstellar space, with its cosmic rays and extreme cold, poses formidable challenges to survival for intact organisms over millions of years. Yet complex organic molecules, which are more robust, can endure in protected niches. 3. I-Atlas, traveling for an unknown span of time between the stars, may have preserved such molecules within its interior, releasing them only now under solar heating. Whether any of these molecules are biologically relevant is an open question. No direct evidence yet indicates the presence of living material in the dust, and such evidence would be extremely difficult to obtain. Still, the interstellar origin of the comet grants its chemistry a kind of independent lineage. Its organics, if present, evolved under a different radiation field, with a different mix of available elements and initial grains. When those organics are finally exposed to the light and fields of the Sun, and some fraction enters planetary atmospheres, a genuine exchange between two stellar environments occurs. Scientific missions have, in the past, captured dust from comets and interstellar space using aerogel collectors flown by spacecraft. These missions show that even tiny grains can carry complex structures and unexpected compositions. The sample script remarks that no similar mission was quickly redirected to intercept 3I Atlas, a missed opportunity in the sense that direct sampling could have transformed speculation into measurement. Without such samples, models of the comet's chemistry must rely on remote sensing and on analogies with other bodies. Even so, the observed data already anchor a set of reasonable expectations: a mixture of water ice, metal-rich minerals, simple volatile molecules including cyanide and related species, and likely a variety of organic compounds assembled over the history of the object. As Earth prepares to move through the diffuse edge of the dust stream, and as Jupiter receives its more distant passage, the question shifts from what 3I Atlas contains in principle to how much of that material will truly interact with planetary environments. It may be that only a small fraction of its dust is captured by Earth, and that the resulting chemical imprint in the atmosphere and in surface deposits is subtle, detectable only in retrospect by careful analytical work. Or, if a denser filament intersects Earth's path, the influx of interstellar grains, rich in metals and organics, could be stronger, leaving a clearer, though still thin layer in geological and ice core records. In both scenarios, the event represents an injection of material from outside the solar system into the ongoing chemical story of Earth. The atmosphere, oceans, crust, and biosphere already contain elements and compounds delivered by past comets and asteroids. The passage of 3I Atlas adds a new chapter, in which chemistry from another star, briefly threads into the cycles of this planet. Its precise effects uncertain, its potential for subtle influence real, and its full story still unfolding in the space between careful measurement and open speculation. The passage of 3I Atlas through the inner solar system does not unfold in isolation from human institutions. Telescopes scan, data pipelines run, archives fill, and behind these visible systems lie policies, budgets, and priorities that decide which questions receive close attention and which are left to fragmentary efforts. The detection of an interstellar object is rare enough that, in principle, it should trigger a coordinated observational campaign across major agencies and observatories. Some of this occurs. Survey projects refine the orbit, large optical telescopes obtain spectra, and space-based instruments such as Hubble contribute high-resolution images that reveal jets and changing structures in the coma. Yet the very fact that the most detailed images of 3I Atlas arrive only when an individual researcher reprocesses archived data from a general-purpose observatory shows that the response is not fully integrated.
The comet is one among many targets competing for time, and its dust stream, which may become most important only months after the nucleus has faded from view, falls into a gap between traditional mission categories. Earth-observing satellites track the atmosphere, space weather missions focus on the sun and its immediate effects, and planetary probes pursue specific objectives at other worlds. A transient interstellar visitor that leaves an extended corridor of dust does not fit neatly into any of these boxes. Into this landscape of partial attention enters a different kind of signal, a response from an intelligence agency to a request for information about 3I Atlas that states that the agency can neither confirm nor deny the existence of relevant documents. This form of wording is familiar to those who follow declassification matters. It is a standard phrase designed to avoid revealing whether an agency has or has not investigated a given topic. In many contexts, it reflects procedure more than content. Yet, when applied to an interstellar object that is actively shedding dust into the path of Earth and Jupiter, it naturally invites speculation. Does such a response simply reflect a blanket policy about ongoing scientific topics? Does it hint at studies of plasma behavior and atmospheric coupling that have been conducted but not made public? Or is it an artifact of bureaucracy, coincidentally phrased in a way that resonates with wider interests in cosmic anomalies? Outside observers cannot answer these questions reliably, and the sample script cautions against reading too much into such statements. Still, the presence of intelligence agencies in the periphery of the narrative serves as a reminder that research into plasma physics, atmospheric effects, and unconventional interactions between dust, fields, and biological systems has often been pursued behind closed doors, as well as in open science. In the public domain, information about 3I Atlas and its dust stream flows through familiar channels. Online encyclopedias, scientific preprints, and data releases from major observatories offer pieces of the picture, but they also carry their own filters and biases. A centralized reference entry might emphasize orbital parameters and basic physical characteristics, while omitting or downplaying more speculative implications about dust interactions and atmospheric effects. Large language models, trained on broad corpora, can summarize known facts, but cannot generate new measurements. They reflect the current state of discourse, including its gaps. The sample script notes that such tools, useful as they are, should be treated with caution, much like any secondary source. Cross-checking with primary data and with the outputs of established analysis pipelines remains essential. For 3I Atlas, those primary sources include telescope archives, spectroscopic survey results, and numerical simulations of dust dynamics. The difficulty lies in synthesizing these lines of evidence quickly enough to inform expectations about the upcoming crossing of the dust stream before it happens, rather than only interpreting it after the fact. The lack of a dedicated sampling mission for 3I Atlas sharpens the sense of limitation. In earlier years, spacecraft have collected dust from ordinary comets and from the interstellar flow passing through the solar system, using aerogel panels to capture tiny particles without destroying them completely. These missions have revealed unexpectedly complex organics and structural diversity in grains that originate both within and beyond the solar system. In principle, redirecting an existing probe or planning a fast flyby mission to intercept the dust of 3I Atlas could have extended this work. One suggestion mentioned in the sample script is that the Juno spacecraft, already in the Jovian system, might have been retasked or its trajectory adjusted to sample the region of space where the debris stream and Jupiter's influence intersect. In practice, mission constraints, fuel reserves, and risk assessments make such rapid changes difficult.
Spacecraft are planned years in advance, and substantial deviations from their design paths can endanger their primary objectives. The result is that, despite awareness of the interstellar visitor, no hardware is positioned to pass directly through its densest dust in a controlled way. Observations remain remote, conducted from Earth orbit and from ground-based facilities. This gap between what could be learned with ideal instrumentation and what is actually being measured leads to a quiet tension. Scientists can describe the general behavior of dust under radiation and gravity, and they can outline plausible ranges for grain sizes, compositions, and trajectories based on spectroscopy and imaging. They can point to known effects of dust streams on meteor rates, atmospheric layers, and satellite drag. They can even model, in broad terms, how charged metallic grains might interact with the magnetosphere. Yet, without direct samples, key uncertainties remain. How exactly does the composition of 3I Atlas dust differ from that of typical solar system comets? Are there organics present that challenge current models of prebiotic chemistry? Do the grains form persistent electrostatic bundles in interplanetary space, or do they disperse more quickly than some laboratory analogs suggest? The answers to these questions bear on estimates of how the stream might influence Earth and other planets, but they remain inaccessible, at least for now. Meanwhile, monitoring systems on and around Earth continue their routine tasks. Meteor radars track the influx of small particles entering the atmosphere, logging their speeds and directions. All sky cameras watch for fireballs. Satellite operators monitor drag and charging effects on their spacecraft. Space weather services watch the sun for flares and coronal mass ejections that can disturb the magnetosphere. To a large extent, these systems are already capable of detecting any major anomaly associated with the passage of the 3I Atlas stream, even if they are not tuned specifically to it. If meteor rates were to spike dramatically during March or April, the change would appear in radar and optical datasets. If satellite drag increased beyond what would be expected from solar activity alone, analysts would notice. If the ionosphere behaved in an unusual way, radio networks and navigation systems would record the effects. The challenge is interpretation. Many of the signatures that might arise from a modest increase in dust flux can also arise from variations in solar output, geomagnetic activity, or changes in atmospheric circulation. Disentangling the contributions requires careful correlation of datasets and, ideally, prior expectations about the timing and magnitude of the dust encounter. In this context, the calendar once again plays a role. Agencies and research groups know, within the uncertainties of current models, when Earth is most likely to intersect the densest parts of the stream. They can pre-plan intensified observation campaigns, arranging to run radars in particular modes, to collect more continuous data from meteor cameras, and to coordinate satellite diagnostics. Some of this planning may be explicit, discussed in workshops and proposals. Some may be informal, driven by interested individuals or small teams who see in the passage of 3I Atlas an opportunity to test ideas about dust stream interactions. Other responses remain opaque, shaped by internal decisions at agencies whose public statements refer only in general terms to space weather readiness and observational priorities. The interplay between openness and silence extends to communication with the wider public. Early coverage of 3I Atlas in media channels often emphasizes its status as only the third recognized interstellar object to pass through the solar system, following the discoveries of the earlier elongated visitor and of the interstellar comet observed in 2019. Headlines focus on its origin beyond the solar system and on the scientific novelty of studying such an object. As the narrative shifts toward the dust stream and the approaching crossing, some outlets highlight the possibility of enhanced meteor activity or subtle environmental effects, while others regard the event as too uncertain or too technical to attract sustained attention. Official agencies walk a line between reassurance and accuracy, acknowledging that Earth will pass through a region of space influenced by the debris of an interstellar comet, while also emphasizing that catastrophic outcomes are not expected. Behind these public messages lies a more granular reality. In research institutes, teams run simulations, compare them with observational constraints, and debate mechanisms such as electrostatic bundling, resonant trapping, and atmospheric chemistry. In less formal settings, independent investigators and enthusiasts explore links between dust streams, historical events, and broader patterns in Earth systems. Some draw connections that remain speculative. Others focus on testable predictions. The presence of ambiguous signals, such as an intelligence agency's refusal to confirm or deny studies related to the object, threads through these discussions as a background note.
It neither validates nor dismisses any particular claim, but it adds to the sense that 3i Atlas sits at a crossroads between open science, classified research, and public curiosity. In this way, the human response to the interstellar visitor mirrors, in its own sphere, the complexity of the dust stream itself. There are regions of high density, where data and analysis cluster, and regions of thin coverage, where only guesses fill the gaps. Institutional structures shape the flow of information, just as gravity and electromagnetic forces shape the flow of grains. At the center of both layers stands the same physical reality: a small, icy, metal-rich body that passed briefly near the sun, released a vast quantity of dust and plasma, and then departed on a trajectory that will not bring it back. The debris it shed now drifts through the orbits of planets and moons, while on Earth, instruments, agencies, and individuals wait to see how and how much this invisible river will make itself known. As the calendar moves into March, the orbits of Earth and 3i Atlas arrange a quiet meeting in space that no human eye can see directly. The nucleus of the interstellar object is already receding, dimmer each week, climbing outward toward the realm of Jupiter and beyond. Yet the corridor of dust and plasma it has laid down remains. Earth, following its regular path, now enters the coordinates where models suggest that this corridor intersects the planetary orbit. There is no boundary line in the sky, no visible front. Instead, the approach expresses itself in probabilities and fluxes. Instruments that have counted an average number of meteors per hour over years may begin to register small increases. The background rate of tiny, invisible impacts on the upper atmosphere may rise. Satellite operators may see gradual changes in drag or charging that do not quite match expected responses to solar activity alone. In most scenarios, these changes are subtle, within the range of natural variability, and only later, when data are stacked and compared, does a pattern emerge. Still, for those watching closely, the knowledge that Earth is moving through the wake of an interstellar visitor adds context to every small anomaly. The timing of the crossing coincides with a broader astronomical season. Around the March equinox, the Sun stands above the equator, and the plane of Earth's orbit intersects the day-night line in a way that makes the faint band of zodiacal light more easily visible after dusk and before dawn. Observers under dark skies see the soft glow rising along the ecliptic, the luminous expression of interplanetary dust scattered through the inner system. Within that glow, grains from 3i Atlas are now mixed, though their contribution is too slight to distinguish by eye. The constellations that frame the night carry their own configurations. At various points around this season, Mars and Venus draw close to the Sun in projection. Jupiter stands in opposition, and distant planets trace slow conjunctions. Astrologers, and those who think in symbolic terms, find meaning in these patterns. Astronomers see alignments that reflect the simple mechanics of orbits. The sample script notes a planetary configuration that places the inner planets in the gas giants in positions that heighten human attention to the sky, whether for scientific or other reasons. The presence of an interstellar dust stream during such a time magnifies that attention further, turning an already charged season into an interval of expectation. Within the atmosphere, microscopic events unfold continuously. Grains from 3i Atlas, most smaller than a grain of sand, enter at high speed, compress the air ahead of them, heat it, and vaporize. The resulting trails of ionization are brief and thin, yet they can be detected by meteor radars and radio experiments that listen for reflections from these momentary columns. Each trail represents the conversion of kinetic energy into heat and light, the transformation of matter from solid grain to atomic vapor. Among the products are metal atoms, such as nickel and iron, simple molecules, such as cyanide, and fragments of more complex organics. These join the existing layers of metallic species in the upper atmosphere, where they participate in chemical reactions that influence ion densities and the formation of delicate, high-altitude clouds. The overall impact is modest compared with the enormous scale of the atmosphere, but real. Over weeks, a measurable layer of interstellar dust settles into longer-lived reservoirs, such as the oceans and ice sheets, where it may one day be identified by careful analysis. Above the atmosphere, in near-Earth space, the flow of dust influences plasma structures in ways that are only partially characterized. Charged grains drifting through the magnetosphere alter local electric fields, trigger small currents, or provide sites for charge separation and reconnection. Electrostatic bundles, if they form in the interplanetary medium and survive into near-Earth space, may perturb the distribution of particles more strongly than individual grains would suggest.
Such bundles could act as coherent packets of dusty plasma, carrying their own internal fields and reacting to the terrestrial magnetosphere as extended entities. Their presence would be subtle, perhaps showing up as small, localized variations in radiation belt intensity, or as transient structures in measurements of space charge. Instruments on satellites, designed primarily to monitor solar wind conditions or radiation hazards, may record such signatures without immediately attributing them to the passage of 3I Atlas debris. Only later, when analysts examine the timing and compare it with orbital models, might a connection be proposed. On the ground, the observable signs remain mostly gentle. Standard meteor showers continue on their regular schedules, driven by long-established streams associated with familiar comets. The increase from 3I Atlas dust, if present, blends into the background, perhaps adding a few extra streaks to all sky camera footage, a slight enhancement that does not rise to the level of a great storm. The spectacular scenario of a sky filled with meteors falling in their hundreds of thousands, as in the historical storm of the early 19th century, remains unlikely given current estimates of the stream's density and geometry. Yet the absence of overt spectacle does not mean that nothing important is happening. The key lies in recognizing that many of the influences involved operate at scales and intensities that require instruments and long integrations to detect. For those who view the solar system as a connected plasma environment as well as a mechanical arrangement of bodies, the passage of an interstellar dust stream through the region near Earth represents an injection of new structure and new material into a network of fields and flows that is already active. Over days and weeks, this injection modulates currents, alters scattering conditions for charged particles, and subtly shifts the parameters that describe near-Earth space. The resulting changes may in turn affect how the environment interacts with human technology and with the upper atmosphere in ways that blend with and modulate the ongoing effects of solar activity. At the same time, in the Jovian system, the more distant portion of the debris stream passes its point of closest approach to Jupiter. Some grains are deflected, some are focused, and a few may become trapped in resonances or in the planet's magnetic environment. The combination of these processes means that 3I Atlas leaves imprints at multiple scales. Local enhancements in dust populations near Earth, modified structures in the broader zodiacal cloud, and minute additions to the rings, clouds, and plasma of a giant planet. Most of these imprints are too small to isolate with current instruments, but their presence is consistent with the physics of dust dynamics and with the known behavior of cometary debris in other contexts. The season of influence extends beyond the immediate months of crossing. Even after Earth has moved on, grains from 3I Atlas that have been captured into heliocentric orbits will continue to drift through the inner solar system. Some will intersect Earth's path in later years, adding a faint interstellar component to the ongoing rain of micrometeoroids. Others will spiral inward and eventually fall into the sun, releasing their stored metals and organics into the solar corona. Still others will be stirred by planetary perturbations into new paths that cross the orbits of Mars, Venus, or Mercury. In this way, the legacy of the interstellar visitor persists long after its core has vanished from sight. Its influence is not a single event, but a distribution of encounters smeared out over time and space. For now, the most immediate focus remains on the initial passage. Instruments record, archives grow, and researchers begin to analyze the first results. Some find nothing beyond expected variation. Others notice minor anomalies that may or may not be related. The connection to 3I Atlas becomes a hypothesis to be tested, one variable among many in a complex system. As conclusions form, they are tempered by the recognition that the stream's internal structure and exact density remain incompletely known. The possibility that Earth has only skimmed the edge of a broader corridor cannot be ruled out, nor can the possibility that future small bodies from interstellar space will follow similar paths with different dust loads and geometries. Each such object will present a new case, a new opportunity to compare theory with observation. The narrative that began with the discovery of a faint, fast-moving point in survey data continued through the revelation of strong jets and a sunward-facing tail, and expanded into considerations of dust streams, plasma bundles, atmospheric chemistry, and institutional responses, does not end with the passage of a date on the calendar. Instead, it settles into a state of ongoing watchfulness. 3. I-Atlas is gone, but the questions it raises remain. How often do interstellar objects carry heavy dust loads through planetary systems? How structured are their debris streams? How deeply can such streams couple into the electromagnetic and chemical environments of planets? And what traces of these encounters accumulate in archives of data, rocks, ice, and perhaps biology? These questions linger in research plans, in mission proposals, and in the quiet work of those who re-examine old datasets with new hypotheses in mind, knowing that the next interstellar visitor may already be on its way, unobserved, laying down its own invisible trail toward the region where planets circle a yellow star.